Hello everyone, my name is Kamil and today me and my friends will talk about the adjustable torque wrench. In this presentation, we will talk about its working principle, its materials, the market research, and then lastly, there's a 3D model animation of the torque wrench. The torque wrench is a brilliant piece of mechanical technology that relies on its internal breakaway system to give us that distinct click sound when the target torque is reached. The internal system consists of three main parts. There is the toggle, which is a small hardened block of steel that sits behind the drive head. And then there is the adjustment screw, which lets us to set the force required to make the toggle click. And then lastly, there is the compression spring, which is a coil spring that pushes against the toggle until the torque requirements are met and the toggle clicks. Here's how the click process works. When we are under the target torque and we pull on the handle, the spring forces the toggle to stay locked in its plates. The wrench acts like a rigid bar. Then, when we reach the target, the torque we apply gradually starts to overpower the linear force of the internal spring. The toggle pivots out of its socket. Then, when the torque requirements are met, the toggle slips out of its pocket and slams into the wall of the metal handle. This sudden impact produces the sharp click we hear.
Hi, I am Enes. Now I am going to explain how torque wrenches work and how the force is distributed during the process. First, let's look at the force transmission path, which shows what happens when we apply force to the wrench. Everything builds on a very fundamental formula. Moment equals distance times force. In this process, it all starts when we apply a physical force to the handle. The length of the wrench arm acts as a lever, converting our effort into torque, which is rotational force. Inside the wrench, there is a spring, and this spring measures this force against the target value. Once that exact target value is reached, the wrench head clicks or stops turning, ensuring the fastener is tightened perfectly. Now, let's move on to force distribution to see where that energy actually goes. There is a very interesting fact here regarding the radial distribution of fasteners. Roughly 90% of our effort is actually lost to friction between the contact surfaces. Only about 10% of effort goes into actual clamping force that holds the parts together. This behavior is calculated using the formula shown on the screen. If we look at the axial distribution, the tie squeeze and highest compression occur right beneath the bolt head and around the washer. As we move deeper into the material, this force naturally dissipates and weakens. Finally, let's look at some everyday examples of average torque applied to see how these numbers look in reality. Different applications require different amounts of power. For example, for delicate tasks like fixing bicycles, electronics, a light torque of 5 to 15 Newton meters is enough. Tightening automotive spark plugs require a bit more effort, ranging from 15 to 30 Newton meters. To keep a car's valve safe, valve lug nuts need a much stronger grip, usually between 100 and 140 Newton meters. And for industrial grade heavy-duty machines, we use massive forces starting from 300 up to over 1000 Newton meters. In conclusion, applying the correct torque is essential for both mechanical safety and material longevity.
Hi, I'm Arda and I'm going to continue with the materials part of our presentation. To better understand the material selection, we can divide the click-type torque wrench into four main functional sections, the outer body and tube, the ratchet head and internal gears, the internal compression spring, and finally the toggle and pivot block. Since each of these pieces is designed for a completely different mechanical purpose, their material requirements differ significantly. Let's start with the outer body. The primary engineering requirement here is high yield strength. When an operator pulls the handle to tighten a bolt, this tube experiences immense bending stresses. We chose chrome vanadium steel because it provides the exceptional yield strength needed to prevent the bar from bending or permanently deforming under heavy industrial forces. Additionally, chrome vanadium offers excellent corrosion resistance over long periods, and its high strength to weight ratio makes it the ideal choice for keeping the tool both durable and manageable. Next, let's look at the ratchet head and internal gears. The gear teeth bear the brunt of concentrated cyclical mechanical forces. To combat this, we use a specialized high-grade chrome molybdenum steel, which is further subjected to induction hardening. Why this specific heat-treated steel? Because our primary objectives here are maximum wear resistance and a high fatigue life. The gears absolutely cannot afford to strip or deform over thousands of cycles, making extreme surface durability non-negotiable for this assembly. The third component is the literal heart of the wrench's accuracy, the internal compression spring. To construct this, we use high carbon spring steel, such as music wire or a silicon manganese alloy steel. We strictly require two things from this material: exceptional elasticity and high creep resistance. If the spring deforms or relaxes over time, the wrench will lose its calibration. This highly resilient alloy ensures that the spring returns to its exact original state every single time, guaranteeing lasting calibration and reliability. Finally, we have the toggle and pivot block, which triggers the physical click mechanism. This part requires a hardened tool steel, specifically O1 or D2 grades. The engineering necessity here is extreme surface hardness. Every single time the wrench reaches its set torque, this block slips and hits the inner wall to produce that signature click. We need maximum hardness so that the contact edges do not wear down or round off after thousands of uses. In conclusion, our material choices prioritize uncompromised strength and fatigue resistance in the internal mechanisms, while smartly balancing durability, weight, and ergonomics across the entire tool. Thank you.
Hello everyone, I'm İrfan Çınar Yazıcı and today I'll be presenting our market research findings regarding torque wrenches, specifically focusing on their costs. In this presentation, we will look into three main areas: average costs, the most expensive versions, and the core cost drivers that determine the final price. Let's start with the average costs. As you can see, we have three main segments. First, consumer and general tools are used for basic tasks and cost between $50 and $2,050. Second, professional and digital devices feature screens for high precision calibration and cost between $3,050 and $1,000. Finally, industrial heavy-duty systems are built for extreme industrial applications ranging from $1,500 to $5,000. Now let's look at the peak models on the market. These premium industrial hydraulic and smart electronic torque systems range from $9,000 to over $19,000. They are highly expensive for two main reasons. They offer extreme torque capacity for massive engineering loads, and the main feature advanced load and data tracking for advanced quality control. Finally, let's break down where this money actually goes. Manufacturing and engineering make up the largest share at 45%, followed by high quality materials and at 25%. Marketing and support account for 20%, and transportation and logistics take up the remaining 10%.
Hello everyone, my name is Ayberk and I will talk about the CAD modeling process of our final project, which is the adjustable torque wrench. We have first started by designing the parts separately in SolidWorks. We have 6 major parts, which are the plunger, the spring, the adjustable knob, the adjustment ring, the main case, and the pivot head. The pivot head sits right above the spring and right below the pivot head, with a male type tip on its head. By that way we ensure that the pivot head's female tip aligns with the plunger's tip, and when the predetermined torque is reached, the spring snaps and the alignment breaks. By that way we hear a click sound. That's basically our project's working principle. So how did we assemble it? We assembled it by making the parts first, as I said, and aligning them on the same central plane, which is the top plane in our case. We aligned them all in the top plane of each other, so that we had a solid tool, which is our torque wrench. That's how we made the solid model. And next my friend will talk about how we have made the animation of it. And as you can see, the animation is here as well.
Hello, my name is Atalay. Today I'm going to present the animation section and conclude the presentation. Now let's dive into the CAD, the core of the CAD modeling of our project, where we brought this mechanism into life in SolidWorks. Our design process began by modeling 6 main distinct components. We engineered a hollow casing with a fork-shaped slot, a pivot featuring a female slot at its tail, a precision plunger to compress the spring, an adjustment ring for user collaboration, a model take spring, an adjustment knob to hold everything in place. For the assembly, every single internal part was nested inside the casing, aligning perfectly with its central rotational axis. To validate this assembly before manufacturing, we created a 3D working animation to test the physical motion. In the software, we established a real physical constant between the plunger and the pivot head. We then assigned the virtual internal spring a realistic linear spring constant of 100 newtons divided by meters. By placing a virtual rotatory motor inside of its pivot head, hole of the head, and adjusting the kinematic parameters, we generated a smooth 4-second engineering animation, as you can see in this loopable GIF. Now let's continue with the conclusion page. To conclude, the adjustable click type torque wrench is a brilliant tool for functional engineering. It remains an indispensable tool across modern industry, crucially preventing the over or under tightenings of fasteners in critical high-stakes applications like automotive assembly and aerospace technology. Now I will finish my presentation. Thank you for your listening and attention.